After studying this module, you shall be able to learn the basic assumptions of VSEPR theory, understand the VSEPR model, be able to predict molecular geometries that deal with Lewis structures containing bonding and non-bonding pairs of electrons, analyze the effect of non-bonding electrons and multiple bonds on bond angles, know the application of VSEPR model for predicting the geometrical shapes of molecules through their Lewis structures, explore the application of VSEPR model for determining the structure of molecules with no central atom. Molecules of different substances have diverse shapes. Atoms attach to each other in various geometric arrangements. The overall molecular shape is determined by its bond angles in space. The shapes of the molecules can be predicted from their Lewis structures as prescribed in the model presented in the valence shell electron pair repulsion theory, which is abbreviated as VSEPR theory. The base of VSEPR theory was laid down by N. V. Sidgwick and H. M. Powell in 1930s, but the modern formulation of VSEPR theory was proposed by R. Nyholm and R. J. Gillespie. VSEPR theory is used for predicting the shapes of individual molecules based on the extent of interactions of electron pairs in the valence shell of the atoms. It explains the shape of the molecules having localized electron pairs, bonded or non-bonded. The shape of a molecule is very important for studying its physical and chemical properties. The VSEPs are regarded as occupying the localized orbitals with proper orientation in space so as to minimize the Coulombic repulsion between the electron pairs, leading to stable spatial arrangement. The stable spatial arrangements of 2, 3, 4, 5 and 6 electron pairs with minimum inter-electron repulsion are linear, trigonal planar, tetrahedral, trigonal bipyramidal and octahedral respectively. Now, we shall see the basic assumptions of the VSEPR theory. The bond angles in a species depend upon number 1, the interatomic van der Waals repulsion amongst the non-bonded atoms. Number 2, the Coulombic repulsion due to partial charges on the atoms due to electronegativity differences, or number 3, repulsion between the electron pairs on the bonded atoms. Of all the three terms, number 3, that is the repulsion between the electron pairs on the bonded atoms, that is the most important factor affecting the geometry of the species. There are three types of repulsions that take place between the electron pairs of a molecule: the lone pair repulsion, the lone pair bonding pair repulsion and the bonding pair repulsion. The repulsion between the lone pair electrons are greater than those between the bonded pairs. For a stable molecule, these repulsions must be minimized. When repulsion cannot be avoided, the weaker repulsion, that is the one that causes the smallest deviation from the ideal shape, is preferred. The order of the repulsion between various types of lone pairs is given as lone pair repulsion is greater than lone pair bond pair repulsion is greater than the bond pair repulsion. This is due to the absence of second nucleus at a distant end of the lone pair. The nucleus at the either ends of the electron pair tends to polarize the electron cloud in the internuclear regions. The lone pair is attracted only its lone nucleus tends to occupy larger angular volume than the bond pair. Further, double bonds occupy more angular space than the single bonds. Also, the bonding to more electronegative substituent occupies less space than bonding to a less electronegative substituent. If the central atom belongs to the third or higher period, the above rules apply for bonding to halogens and oxygen atoms only. For other atoms, the lone pair occupies non-bonding s orbitals and bonding is through p orbitals. Example in the phosphine, bond angle 94 degrees, or in arsine where the bond angle is 92 degrees. The valence bond theory and VSEPR theory is usually compared with each other. The valence bond theory deals with the molecular shape through orbitals that are energetically accessible for bonding and mainly concerns with the formation of sigma and pi bonds. Another model named molecular orbital theory also describes that how atoms and electrons are assembled into molecules and polyatomic ions. VSEPR theory was structurally accurate and molecular geometries of covalent molecules have been predicted successfully. VSEPR theory has been criticized for not being quantitative. The shape of a molecule can be related to the following 5 basic arrangements. We can see in the table we have the number of electron pairs, the arrangement of electron pairs, the electron pair geometry and the predicted bond angles. For 2 electron pairs, we have the linear geometry with bond angle 180 degrees. For 3 electron pairs, the geometry is trigonal planar with 120 degrees bond angle. For 4 electron pairs, the geometry is tetrahedral with bond angle 109.5 degrees. For 5 electron pairs, the geometry is trigonal bipyramidal with bond angles 90 degrees and 120 degrees. And for 6 electron pairs, the geometry is octahedral with bond angle 90 degrees. Now, we shall have a look at the valence shell electron pair repulsion model. As discussed earlier, the VSEPR model helps in predicting the molecular structures where atoms are bonded together by electron pairs in valence orbitals. Since electrons are negatively charged species, they tend to repel other electrons present as lone pairs. Bonding pairs of shared electrons tend to repel other bonding pairs of electrons in the valence orbital. The factors that affect the geometry of the molecular species are number 1, the total number of electron pairs in the valence shell of the central atom, number 2, the availability of the low energy orbitals, and number 3, the lone pairs. The lone pairs are assigned the positions where lone pair repulsions are minimum, and lone pair can expand more readily due to the larger angular volume. Table gives the shapes of the molecules predicted from the VSEPR theory. Here are some examples of species where the d orbitals are not used. Isoelectronic CH4, NH3, H2O, HF and NH4 plus. In all of these, the central atoms uses sp3 hybrid orbitals. In CH4, that is methane, all the orbitals have bonding pairs resulting in a symmetrical structure with bond angle 109.5 degrees. Ammonia NH3, water H2O and hydrofluoric acid, that is HF, have 1, 2, 3 lone pairs respectively. The increasing lone pair repulsion decreases the bond angle from 109.5 degrees to 107 degrees in ammonia to 104 degrees in water, as shown in figure shows the structure of methane CH4, ammonia NH3, water H2O, hydrogen fluoride and ammonium ion from the valence shell electron pair repulsion theory. When a proton gets attached to the lone pair of NH3 and forms NH4 positive ion, the lone pair gets polarized by the positive charge of the proton and gets concentrated along the NH axis. Due to the decreased electron density around nitrogen atoms, the 3 bond pairs open up, and as all the 4 electron pairs are now bond pairs, a symmetrical tetrahedral structure with bond angle 109.5 degrees results. The positive charge of the proton is equally shared by all the 4 protons. Now, let us discuss about the geometry of species which involve the d orbitals. Let us consider the species PF5, SF4, ClF3 and ICl2- ion having 10 electrons each in the valence shell of the central atom. The lone pairs present on phosphorus, sulfur, chlorine and iodine are 0, 1, 2 and 3 respectively. the 10 electrons are housed in the trigonal bipyramidal geometry, that is in the sp3d hybrid orbitals. Figure 2 shows the possible geometries of A. Phosphorus pentachloride PF5, B. Sulfur tetrafluoride SF4, C. Chloride trifluoride ClF3 and D. Dichloroiodate ion ICl2- on the basis of VSEPR theory. Compounds with highly electronegative fluorine, which creates partial positive charge on the central atom and reduces the size of the d orbitals. Role of outer d orbitals is in the compounds like nitronium, that is NO2 plus ion, nitrite, that is the NO2 minus ion, the splitting of d orbitals should take place. This depends on the energy of d orbitals and their diffused nature. Outer d electrons are used only in the case of formation of larger number of bonds, 5, 6 or 7, compounds with highly electronegative fluorine, which creates partial positive charge on the central atom and reduces the size of the d orbitals. Figure shows the VSEPR pictures of nitronium ion, that is NO2 plus ion, the nitrite ion, NO2 minus ion and the free radical NO2. Now we shall see how do we predict the molecular geometries. For determining of geometry of the molecule with the help of VSEPR model, various steps involved are: number 1, write down the Lewis dot structure of the molecule. Number 2, count and arrange the total number of electron pairs around the central atom. The arrangement should be done in such a way so that the valence shell electron pair repulsion can be minimized. Number 3, describing the molecular geometry in terms of angular arrangement of the bonding pairs. In Lewis structures, there are two types of valence electron pairs: bonding pairs, which are shared by the atoms in the bonds, and the non-bonding pairs, which are also called the lone pairs. Let us consider the Lewis structure of ammonia. Ammonia contains 3 bonding pairs of electrons and 1 non-bonding pair, that is the lone pair. The ammonia has distorted tetrahedral geometry because in this arrangement the electron pair repulsion between these 4 electron pairs is minimum. This arrangement is for the valence electron pairs. What about the atoms in a compound? The molecular geometry is the location of the atoms of a compound in space. We can predict the molecular geometry from the electron pair geometry. We can see in the table total number of electron pairs, electron pair geometry, the total number of bonding pairs, the number of non-bonding pairs and the molecular geometry. For 2 electron pairs, we have the linear geometry. For 2 bonding pairs and 0 non-bonding pairs, and the molecular geometry is also linear. For 3 electron pairs, when the bonding pairs are 3 and non-bonding pairs are 0, we have the electron pair geometry and the molecular geometry both as trigonal planar. But when the electron pairs are 3 and the bonding pairs are 2 and non-bonding pair is 1, the electron pair geometry is trigonal planar, but the molecular geometry is the bent. Similarly, for total number of electron pairs 4, we have different arrangements that are possible. When the bonding pairs are 4 and there is no non-bonding pair, the electron pair geometry and the molecular geometry is tetrahedral. When the bond pairs are 3 and 1 non-bonding pair is there, the electron pair geometry is tetrahedral, the molecular geometry is trigonal pyramidal. And when the bond pairs are 2 and the non-bonding pairs are 2, the electron pair geometry is tetrahedral and the molecular geometry is bent. Now we shall see 4 or fewer valence shell electron pairs. Here we will try to understand some molecules or ions which obey the octet rule. We should note that in the prediction of geometry of the molecule, a double or triple bond is counted as one bonding pair. For example, using the VSEPR model, we can predict the geometries of SnCl3- ion and O3 molecule. The SnCl3 ion is trigonal pyramidal and the O3 molecule is bent in nature. Now we shall see the effect of non-bonding electrons and multiple bonds on bond angles. VSEPR model can be used to explain certain exceptions from ideal bond geometries observed in some structures. For example, in the case of water, methane and ammonia, it is assumed that all have tetrahedral electron pair geometries, but ammonia and water are slightly distorted from an ideal tetrahedron. This is shown in the figures. The bond angle decreases as the number of non-bonding electron pairs increase. When the central atom has d orbitals available, then it may have more than 4 electron pairs around it. Such central atoms exhibit a variety of molecular geometries. We can see that when the bond pairs are 5 and non-bonding pairs are 0, the electron pair geometry is trigonal bipyramidal, but the molecular geometry is also trigonal bipyramidal. But when the bond pairs are 4 with one non-bonding pair, the molecular geometry turns to be seesaw. When the bond pairs are 3 and non-bonding pairs are 2, the molecular geometry is T-shaped, and when the bond pairs are 2 and the non-bonding pairs are 3, the molecular geometry is linear. For the electron pairs number 6, we have the electron pair geometry is octahedral. The molecular geometry is also octahedral when the bond pairs are 6 and the non-bonding pairs are 0. But when the bond pairs are 5 and one non-bonding pair is there, we have the square pyramidal geometry. And when the bond pairs are 4 and the non-bonding pairs are 2, we have the square planar molecular geometry. The trigonal bipyramidal arrangement for atoms with 5 pairs of valence electrons contains two geometrically distinct types of electron pairs, axial and equatorial. We can see in the figure that in the trigonal bipyramidal geometry, the axial electron pairs are 90 degrees apart and the equatorial bond pairs are 120 degrees apart. If there is a non-bonding pair of electrons, a larger electron crowd, it will go in the axial position to minimize the electron repulsion. The octahedral structure contains 6 pairs of valence electrons. All positions are equivalent and at 90 degrees from one another. If there is one non-bonding pair of electrons, it makes no difference where we place them. However, if there are 2 non-bonding pairs of electrons, the second pair will be 180 degrees from the first to minimize the steric interaction. Now we shall see the molecules with no central atom. Let us consider acetic acid. The first carbon has 4 pairs of valence electrons and will be tetrahedral. The second carbon has 3, that is multiple bonds count as 1 in VSEPR and will be trigonal planar. The oxygen on the right has 4 and will be tetrahedral, only has 2 bond pairs and thus it will appear as bent conformation. Now we shall see the limitations of VSEPR theory. Though satisfactory for many species, the VSEPR theory fails for most of the 14 electron systems. For IF7 and REF7, where no lone pairs exist, the expected structure is pentagonal bipyramidal with sp3-d3 hybridization. It fails to explain the species with lone pairs. Thus, it does not give a correct structure for XEF6 or SBF6-3- distorted octahedron in which the lone pair is trying to emerge out of the triangular phase. IF6-, the lower symmetry octahedron, PB2, AS3 and sp3 complexes with hexadentate ligands, pentagonal bipyramid where the lone pair seems to occupy the axial orbitals so that it appears that in these complexes the lone pair occupies less space than the bond pairs. Further, though the alkaline earth halides are ionic in a solid state, they are covalent in the vapor state, whereas some of them have a bent V shape. This cannot be explained as the alkaline earth ions after the formation of dihalides do not have any electron pair on them. Generally, it fails to predict the shapes of isoelectronic species and transition metal compounds. This model does not take relative size of substituents and stereochemically inactive lone pairs into account. This can be seen in figure which shows the structure of XCF6 and SPF3 in which the lone pairs of electrons is emerging out of the triangular phase. Now we shall summarize what we have learned in this module. This module discusses about the following things. The valence shell electron pair repulsion, VSEPR theory, helps in the prediction of geometries or shapes of the molecules from their Lewis dot structures. The basic assumptions of VSEPR theory, which state that the electron pairs are negatively charged and repel each other. The VSEPR model helps in the prediction of molecular geometry. The best spatial arrangement of the bonding pairs of electrons in the valence shell is the one in which the repulsions between the electron pairs are minimized. Predicting of molecular geometries from Lewis dot structures containing bonding and non-bonding pairs of electrons. The effect of non-bonding electron pairs and multiple bonds on the bond angles of the molecule. Application of VSEPR model for determining the structure of molecules with no central atom.